So thanks for our second talk this quarter. We have another excellent theory research faculty. Ohad has been here already. This is your third year at TTIC, and working with fine-grained complexity, and will tell us today about some of his new results. Thank you.
Thanks.
Oh, sorry. And also the microphone is unmuted, and so anything you say will be recorded. Sorry about that.
Thank you very much. It's actually not precisely new results, but more like kind of an overview. It's my job that I've been focusing on in the last few months. All right, so the subject of algorithms design can be divided into two time periods. Arguably, the first one is since the 1970s, where the goal was to decide whether given a problem, whether it is polynomially solvable or it is NP-hard. And if a problem was, it was concluded that the problem is in P, then people thought, okay, that's easy, we're good, we're happy. And if it was proved NP-hard, then maybe not so much. And the second time period, maybe since the 2000s, because of big data, so there was a new demand that implied that polynomial time algorithms are now slow in practice because the inputs are bigger. So just having an n squared or n cubed or just a polynomial time algorithm wasn't really cutting it. And so the goal would be to find faster and faster algorithms, right? So even if the algorithm is polynomial, you want to make it even faster. However, the problem is that the progress in developing new algorithms is often stalled. And so what we wanted to do in that case is to explain why we cannot make sufficient progress. And the reasons for that are multiple. Two of them are first to prevent waste of research time. So if there is a good reason for why a problem cannot be solved faster, we want to know it and maybe guide research time in other directions. And the second, another reason is to change the model, which means that if a problem in practice is typically modeled in a certain way into a theoretical kind of a framework, theoretical problem, and now this theoretical problem seems difficult, then maybe you want to do the modeling again. Maybe you want to find another way to capture the issue, capture the problem. But how can we prove that some algorithms do not exist? There are many, and it wasn't clear. So what are we doing? So similar to NP-hardness, where you had one problem that was proved difficult, and then given that, we managed to show that many other problems were difficult. So for SAT, right, it was proved NP-hard, and then many other problems were proved as well. One might think maybe you can mimic that for problems in P. You want to find maybe a canonical problem, and then reduced to many other problems and have similar kind of consequences. If you make progress in one, you would break a lot of barriers. And the issue is that no such problem is known, and this is a essentially where fine-grained complexity enters the scene. And so the motivation is to classify the time complexity of the many central problems in P. Problems that are polynomially solvable, you want to still know what is the right time for them. It could be n cubed, n4, etc. Okay? And more technically, the way that it goes is by connecting the many problems in P via subtle reductions, what we call fine-grained reductions, to just a few hardest assumptions. So again, if one makes progress in any one of those problems in P, you would break some of those hardest assumptions. So you would have just a handful, let's say, of hardest assumptions, and then given those, you would get those conclusions for many problems in P. Okay? And just to give you some examples, so those problems on the left are considered maybe the main hardness assumptions in finite complexity. You have SETH, maybe you've heard of it, the strong exponential time hypothesis, essentially saying that SAT needs 2 to the n time to be solved. And given this assumption, you have many hardest assumptions for problems in P. Like orthogonal vectors with k groups, for example, need n to the k, or edidistance need n squared, etc. Similarly with all pair shortest path or threesome. So it's a very popular field in the last decade, and all of those reductions are from this. Most of these reductions are from this time period.
So sorry. So
yes.
For each one of these, what's the assumption? So
yeah.
What's the assumption of runtime? So basically, the assumption that runtime exactly matches the best known or kind of the naive algorithm.
Yes. So SETH is 2 to the n. APSP, all pair shortest path, is n cubed, right? And then, given that assumption, you have you have conclusions for the problems on the right.
Okay.
So it's not always the same running time. For example, SETH is 2 to the n, and then you get something that is polynomial, right? But yes, it's, essentially, you want some like concrete exponent. Something like that.
Just out of curiosity, what's the result for edit distance?
N squared. Yeah.
So if you have any better algorithm for edit distance, then you will automatically break SETH.
Yes, it would be a huge breakthrough.
And it's a normal reduction. I give you one algorithm and you construct another algorithm by
yeah, it's immediately. The algorithms for SETH would follow right away. Yeah. Any algorithm.
Yeah.
Okay. All right, so in this slide, I want to say that the relationship is, there is some kind of a symbiosis between faster algorithms and lower bounds. So,
sorry,
yes.
I just got a question. I'm curious, what's your level or the community level of confidence in these assumptions? Like P equals NP, there's probably extremely few optimists left. But here, like, how shattering would it be if you could do like all pair shortest path and like n cubed over log n?
That's a very good question. So first of all, really 99% of the reductions that we're talking about are not about logs. It's about polynomial progress, right? So the assumption is that you cannot solve APSP in n to the 2.99, okay. Right? And how shattering would it be? Well, some of the assumptions you have more people believing than others. I think APSP is quite believable. SETH maybe not as much. Threesome. So it depends on the problem, on the assumptions exactly. I think within the finite community, any such result would be amazing. And given how popular the field has been in the last 10 years, I think it would be like the entire community would be very interested in knowing such algorithm.
Or the reduction both ways? Like, would improvement in all-pair shortest path immediately solve also the other problems?
That's another great question. So in some of those reductions, it's only one way. Usually in I think SETH and some of the reduction from threesome in APSP, actually it's usually in both ways. So yeah, you have with the negative triangles, radius, median. You have both ways. You break them, you break SPP, and vice versa.
Thanks.
Sure.
Not you asked my question.
So, are there fine-grained complexity problems where progress would, like, I don't know, if we get a better algorithm for all-pair shortest path, that would imply something about P versus NP? Like, is there something that goes in the other direction?
No. I think it's it's an interesting question because the running time is n cubed. So usually it's quite easy to go from up to low, from SETH, which is 2 to the n, then to low to polynomial algorithms. You create some instance with maybe 2 to the n over 2 input size, and then if you solve it faster than n squared, and n here is 2 to the n over 2, then you get something. But usually the other direction is quite difficult. I'm not aware of such reductions, natural reductions. Yeah. So what I want to say here is that there is a symbiosis between fast algorithms and lower bounds. So if you try to, so what this field maybe helps as well is if you try to design faster algorithm for a problem, you cannot, then you have maybe a broad enough list of hardness assumptions that maybe you can show a conditional lower bounds, at least for one. And also the other direction has been quite successful. If you try to show lower bounds and you cannot, then oftentimes it leads to faster algorithms because you get some insights. I'm going to talk about that as well in the remaining of the talk. So what are central problems in graphs? About we can talk about shortest path and maximum flow, matching, global minimum cut. Then specifically maximum flow. This is not a general audience here, I would assume, and so we all know max flow. It's a pretty basic problem. So let me go quickly. Let me just remind you that the value of the maximum flow from S to T is also the value of the minimum cut by the min cut max flow theorem. Okay, and now this has been a problem of interest for me for the last years. It's called the all-pair maximum flow. In this problem, we're given a graph, maybe with capacities, and then we want to output for every pair of nodes the maximum flow that can be shipped between them.
Not concurrently, right? So you're like...
Yeah, exactly. You have n squared instances, so to speak, yeah? And it could be the values, it could be cuts, maybe in a data structure way, depending on the exact questions. Okay, now, why is this problem interesting? So I can name a few reasons. First, it's a sub-Routinian algorithms for central problems. It has been used for approximation algorithm for minimum k-cut, matching, etc. And it's of practical use. Again, it has been used in image segmentation, clustering, communication, social networks, etc. And just to give you a recent example, this is Japan. This is central Japan. And in a paper from 4 years ago, they used all-pair max flow in order to identify weak spots in the road network. You can see them in red rectangles are weak points. So maybe you wanna add roads in those areas so that people are not stuck if there are too many cars on the road. Example. Now, as far as more in the direction of theory, arguably it's interesting also because we can think of it in comparison with the all pairs shortest path problem. So if we're talking about one pair of nodes, just one pair S and T, then algorithms for shortest path are arguably simple and they are strong. They can output many values at once. Even if you just care about the shortest path between S and T, you could get, in some algorithms, for example with Dijkstra, you can get the single source all things value, right? You want the value to get from S to T, you get from S to everybody else. And as opposed to that, with maximum flow, this is not the case. Algorithms are more complex for single pair max flow, and also no algorithm that I'm aware of is doing anything else but just outputting the value for the single pair. So it seems more difficult for single pair. And then the question is, if you go to all pairs, if that remains the case, is it still the case that all pairs max flow would be more difficult than all pairs shortest path? Yeah.
So in the case of single source all sinks, is a nice structural property, like there's a single tree, right? That you have a single source, you can in one tree you can describe the shortest path to all the sinks.
Yeah.
Is there a comparable thing for flow? So for single source, every possible sink, is there a compact way to describe all the cuts?
Yes, there is. In some of the settings that I'm going to talk about next, if the graph is undirected and edge capacitated, there is a data structure called Gomori-Hu tree, which captures all of the cuts in the graph, but it still doesn't have this effect that you want to get just the answer for one pair and you automatically get all of them. So is it more difficult? And so now I'm going to focus exactly on that, on Gomori-Hu, and I'm going to show how the tools of finite complexity can also lead to new algorithms. Okay, so again, all pairs maximum flow, given a graph, you want the maximum flow between every pair. The Gomori-Hu tree is a succinct data structure for this problem where the given graph is undirected again and edge capacitated. Capacities are on the edges. Specifically, this data structure is a tree on the same set of nodes as the given graph. So that given a pair ST, you want to find the minimum cut between them in the graph, you just go to the tree. We ask the question there, and then you get the answer for the graph. So I'm gonna yeah.
Oh, you get the value of the cut, or you get the actual cut?
Both. Yeah, you have two definitions of Gomori-Hu trees. The one that I'm talking about, you can get both. So here's an example. Let's say you have the graph on the left, and on the right you have the Gomori-Hu tree, right? And let's say you want to find the minimum cut between the pair of nodes 2 and 7 in the graph. So instead of focusing on the graph to find the answer, you just go to the tree. And in a tree, finding a minimum cut is quite easy. And so in this case, it's going to be just the edge, the lightest edge on the path between the two nodes. It's going to be 5. So you immediately get the value of the cut, but you also get a weakness, you get the cut. By removing this edge, you get the partition of the set of nodes of the graph. Then in the graph, it's going to be a minimum cut. Yes, please.
Is there any particular reason you are talking here about mean cuts, not max flows?
Well, it's the strongest version of the Gomori-Hu tree.
Why?
Oh, there are two versions. There is one that preserves the cuts themselves, like I described now, and there is another one that only preserves the flow. And
The flow value, you mean?
just the flow value, sorry, yes.
Oh, flow value, but not flows.
No flow, not the cuts. Flows, anyway, these structures are not talking about flows at all. There are other structures that can maybe talk about flows, but not what I'm talking about. Yeah. Cuts or cut values, or flow values. Okay.
Wait, sorry, I'm just trying to understand. So, in terms of access, that means I can, after computing this, in linear time, I can find the cut in linear time. Is that correct? Do I understand? I'm just making sure I understand correctly.
Yeah. Well, if
how
you
it uses
if you
once you give me this data structure,
yeah.
this allows me to find the max cut between any two nodes
Min
in
cut?
linear time.
Min
The
cut?
min cut between any two nodes in linear time.
Yeah.
Is that correct?
The reason I'm hesitant, you can do even better.
Uh-huh.
If you want to actually show all of the nodes and where they are, then yes, linear time. But if you just want the edges, it could be smaller. If you just want the value, it can be much smaller.
Oh, you're saying linear number of nodes.
Linear number of, yeah, well, I mean, if you want the partition itself, then linear number of nodes you cannot get out of it, right?
Yeah, exactly.
Yeah, I'm saying that there are other type of
If the
answers.
graph is wait, how can I get less than linear number? What can be how can I get less
No,
than
if you
linear
want just
nodes?
the edges in the cut, for example, you can have, I don't know, 11 edges, you can just show them instead of showing the entire partition of the set of nodes. Just the edges in the cut. I'm saying that there are
How
other.
do they do that in less than linear time? Linear number of nodes time.
It's linear number of edges, but not.
No,
It
because
It could be that the number of edges in the answer is much smaller than linear.
that's true, but how can I find it? But what you're showing us would require still linear number of nodes time.
Well, you can do some pre-processing in order to be able to
Okay.
just answer with the edges and not
Okay, but using other methods beyond what
Yeah,
you're
yeah,
showing us. Okay.
Yeah.
Are you going to tell us how to build that?
No.
This is like this amazing thing.
You just convinced us this is like the most central thing with all these applications. You're not going to tell us how to do it?
Yeah, it's actually
You completely sold us on it.
I mean, it's a textbook algorithm, the Gomori-Hu. It's like 60 years old. I mean, I can say in a few words how it is done. This is not the focus.
Okay.
Yeah. So this tree, Gomori and Hu, showed in 1961 that it exists. So it's not obvious that this tree exists even, right? So they showed it exists, and also they show that it can be found in the time of n applications of maximum flow between a single pair. So this is T of m, and this is the number of edges. T of m, the time of maximum flow between a single pair of nodes. So you apply it n times, this is the running time. Right, so this has been the running time for the last roughly 60 years.
Can you remind us what's TM?
TM is the time of the maximum flow for a single pair.
Which is?
Oh,
a bit more.
Yeah, in the last few years, we know that it's near linear, and it's been going down steadily throughout the years. Yeah, yeah.
Is there also a notion of an approximate Gomori-Hu tree?
Yes, but spoiler alert, it's not needed anymore
Okay.
because it can be solved in near linear time.
Good question.
If I just want 1 plus epsilon approximations of cut values, is there a better tree?
Given this running time, it would make sense,
Okay,
and people did do it. We did do it, but now that it can be solved fast, maybe it makes sense in, I don't know, sublinear algorithms or something else that is not. Okay, so I'm going to describe the journey, let's say, of how we got a faster algorithm for this problem. So So first, we considered the problem, the all-pairs maximum flow problem, in more difficult settings in order to get a sense of when the problem might be hard to solve. Right? For Gomer-Hu tree, no conditional lower bounds were known, so we thought it makes sense to consider the problem in slightly more difficult settings. Maybe so Gomer-Hu tree, as we said, exists if the graph is undirected and edge capacitated. So maybe you want to consider directed graphs. The capacities are on the nodes versus the edges, and so forth. And we did manage, we and others, we did manage to show conditional lower bounds for those other settings. For example, in sparse graphs, there is directed and edge capacitated. We showed that it requires n³ time in order to find those all-pairs max flow values. Assuming the SETH that we just discussed, the strong experience time hypothesis, if you assume it requires 2 to the n time, then you get, with this reduction from SETH, from SAT, that all-pairs max flow, in order to solve it, you essentially have to just naively find all of the answers. Just n² applications of maximum flow, which is n³ in sparse graphs. This is essentially the best possible, assuming SETH. Yes, you wanted to ask something?
Is there a reason that you need SETH and not just ETH?
Yes, ETH is doesn't assume anything about the concrete constant in the exponent, right? It just assumes 2 to the yeah, and so it is typically helpful in NP hardness more, not specifically in fine-grained complexity, right? Because you do need the more precise constant in order to show that n³ this is the running time, not like this is.
Do you need do you use the k-sat when k goes to
Yes, this is I didn't wanna go to these details, but yes, this is a more precise definition of SETH. That k-sat, as you go with k, as k goes up, the running time required is closer to 2 to the n. Yeah.
I'm a bit lost about the first result. How does it compare with the upper bound n times t of m? If it is sparse, then m is like n.
Right. So this is harder settings. This is not the Gomer-Hu setting. So you don't have an algorithm doing that in n applications of max flow, but you just have a naive algorithm. N² application. So for each pair of nodes, you just ask what is the maximum flow between them. So it's n² times m. The graph is sparse, so m is n, right? So n² times n is n³. And this is tight with the conditional lower bound.
I think what we're confused about, because I was also actually confused until I looked it up a second ago. So here what's harder here is it's undirected.
What is harder?
Is it directed versus undirected, or what's harder? I mean.
Yeah. So what is harder is that it is not a setting where Gomer-Hu tree exists.
What are those settings? Which is undirected? Right?
Anything that is not undirected and edge capacitated. So this, if you have these two.
What do you mean by edge capacitated? What do you mean by not edge capacitated?
You could have capacities on the nodes and not on the edges, right? So,
okay.
For example, right? So you can have so if the setting is that both the graph is undirected and edge capacitated, then it's easy, Gomer-Hu, good. Anything else is harder, more difficult. You don't have a succinct data structure. I mean, sometimes you do have algorithms that are faster than the naive approach, but it is still more difficult. So what I'm saying here is that for example, for directed graphs with edge capacities, we showed an n³ conditional lower bound.
So Gomer-Hu works, you say, only for undirected graphs.
With edge capacities, yeah. If you have undirected graphs with node capacities, then Gomer-Hu tree doesn't exist.
Okay, but that's basically directed. I mean, the node capacity is like you just put a directed data, right? I mean,
If you can show it, then you will have a nice paper, I think.
Wait, sorry, maybe
I can say more.
talk afterwards.
Yeah, I'm saying that there are some algorithms that are better for node capacities and don't work for edge capacities. For example, if we're talking about unit capacities, all-pairs max flow unit node capacities, you can solve it in m squared time, and you cannot do it for edge capacities, for example. All right, so I'm saying that there are examples.
No, sure, but okay.
Yeah. Okay. Okay. Any more questions on this? And okay, so secondly, for dense graphs, all-pairs max flow in dense graphs, we show that it requires n to the omega plus 1 time, assuming the four-Klee conjecture. Now, omega here is such that multiplying two matrices requires n to the omega time. It's omega is around 2 to 2.3 something, I think. And the four-Klee conjecture is saying that given a graph, you want to know whether there is a four-click in it, you have to spend n to the omega plus 1 time. What it meant is that, so we can talk about combinatorial algorithms that don't use those fast matrix multiplication methods, or divide and conquer Strassen-like methods. And if you assume those algorithms, then you get here n to the fourth time lower bound, assuming the four-Klee conjecture. Right? The four-Klee conjecture, you have to spend n to the fourth time if you don't use combinatorial. If you only use combinatorial algorithms and don't use fast matrix multiplication methods, and so and that would also mean that the naive approach is the best. Again, if you just restrict yourself to algorithms that do not use fast matrix multiplication methods, and I will say that this asterisk here is because it goes back to your question that this assumption doesn't seem like it holds. But it's not published yet. It's a result of Omri Weinstein from the Hebrew University and Kevin Pratt from NYU, I think, and Yael, their student of Omri. It's not published yet, but I don't know. Yeah.
You talked about these matrix multiplication algorithms. Is there a clean model of computation that rules those out?
Unfortunately, no. No, it's not well defined. It's not well defined.
But you have to prove a theorem.
Hmm?
You have to prove you're saying you're going to prove a theorem that under that assumption.
Yeah.
This, the terms with omega.
Yeah. If you want to say that omega is 3, then you're going to this philosophical area, like arguments. But otherwise, yeah.
So just correctly, the theorem is the first bullet is omega plus 1 minus O of 1.
Yeah.
And that second bullet is more like hand wavy. It's not a theorem.
Yeah.
Right?
Yeah.
So maybe it will also answer David's question. So if alpha is, for example, is what you can get best for click, regardless.
You said, I'm sorry.
What?
Can you please repeat the question?
Alpha. Let alpha be the best constant you can get for click conjecture with any method, whatever, matrix multiplication or whatever. Can you replace your bound with n alpha minus little of 1? Do you simply have a reduction from for-Klee conjecture that doesn't care about matrix multiplication?
You're asking if the running time would be tight. If you have any running time for all-pairs max flow, would you get the same thing for click? Or maybe you have some losses during this reduction.
Okay, so I give you any algorithm for the for-Klee conjecture, whatever, that run maybe not based on matrix multiplication, which runs in time n to the alpha. Does it imply an algorithm for this program?
Oh, you're asking if there is a reduction in the other way.
Yeah, that's what it
What I'm
says,
saying
right?
is the opposite. If you have an algorithm for all pairs max flow, then you have an algorithm for click. I think if I understand I think if you understand you're asking the opposite direction, right? If
No.
Oh, you're asking this.
The same direction.
Right.
I give you an algorithm which runs in times n to the alpha, where alpha
Let's say alpha is
some constant.
3.5.
Alpha is whatever.
Yeah.
Then you will get an algorithm for click conjecture so that you don't have to talk at all about matrix multiplication.
Yeah.
It's possible, yeah?
Yeah. This
It's
is,
purely combinatorial, yeah?
if the algorithm that you have is pretty combinatorial, then yes.
Okay,
this
good.
is
good,
precisely
good,
what it
good,
means.
good,
Yeah.
good. Then it might be simpler to avoid here talking about matrix multiplication at all.
Okay.
This is very inherent to the argument here. I'm
We
sorry.
have about 15 minutes, so just
Oh, sorry.
feel free to ignore some of our questions.
Thank you. Okay. So the second step is we design a non-deterministic algorithm for Gomory-Hu trees. Now you might ask, why non-deterministic algorithms? What does it have to do with anything here? So first, what is a non-deterministic algorithm in this context? It's an algorithm that can make guesses, and then eventually it would output a correct output, or it says, I don't know. And we also want that for every input, there is a correct guess. So in our case, for every graph, there is a Gomory-Hu tree, and so a guess would lead to a correct output. There is a guess that would lead us to a correct output. And specifically what we did was we showed a near linear time non-deterministic algorithm in simple graphs. And the consequences of that were first, given a known framework in fine-grained complexity, we got what is called an irreducibility result for Gomory-Hu tree. So this means that a reduction from ACTH to the construction of Gomory-Hu tree would be unlikely. That's what it means. Irreducibility. It's unlikely to have a reduction. This is a known framework that I'm not going to talk about now, but this is essentially a conclusion of it. But another conclusion, another point is that in this non-deterministic algorithm, we got an algorithmic insight. So even though it is much stronger, right? But still, it was interesting to know that the single source max flow problem already captures the hardness of the all pairs version, right? So we can call back the shortest path situation and see that here it is kind of maybe rigorously we can tell that the single source is just as difficult as the all pairs version, but still just in the non-deterministic for non-deterministic algorithms. Third, we showed that these algorithmic insights hold in the standard model as well. So not just non-deterministic algorithms, showed proof that the Gomory-Hu tree can be constructed fast, if and only if single source max flow can be computed fast. Right? If there's a data structure for this, just the single source max flows, then if you can construct such data structure fast, then you immediately get a Gomory-Hu tree. It's an if and only if relationship.
A little bit fast is like
Near linear. Yeah, I mean,
linear. I mean, okay.
yeah, we did have some. I mean, if it wasn't near linear, then you would also get something else for that. But yeah,
Okay.
this part was about near linearity or not. Okay. And then, given this insight, we focused on a very restricted setting. We showed that where the hardness lies. So even if the graph is simple, unweighted, we got that if this is its Gomory-Hu tree, then it is difficult to find. So this is where the difficulty lies. So if you are guaranteed that for your given graph, the Gomer-Hu tree looks like that. And even if you're given the identity of P, the pivot, and a list of the parents, L1, and a list of the L2, the grandkids, it's still getting the precise identities of the nodes would be difficult. As difficult as Gomer-Hu tree. And then focusing on this example and then going back to the general setting, we managed to show the first subcubic algorithm for the problem in simple graphs. We showed into the 2.5 time algorithm, which is faster than n applications of maximum flow, which would be n cubed, n times m n squared. So the main tool that we discovered was it's called the isolating cuts lemma. This is what we use to solve the single source. Then with this reduction to single source, managed to solve the entire problem. This lemma was independently discovered by another group, but in a different context of global minimum cuts.
Just the lemma, or I'm curious, were they also looking at fine-grained complexity, or they had completely different motivations?
They had no fine-grained complexity as far as I'm aware of in their just global minimum
And
cuts.
this is just the lemma, not the algorithm.
Yes,
Yeah.
just specific lemma that is proved quite useful. I'm going to talk a little bit about it if I have the time.
You don't.
I don't.
Yeah, so maybe you do. We have 10 minutes.
10 minutes. Okay. So I'll say that this running time was subsequently improved, right? So we published this result. Then the next conference, several groups, including ours, showed algorithms, faster algorithms.
Sorry, wait, why do you need the n? When do you need the n to the 2 and 8 if you have an n squared?
Well, because it was independent, this works.
Oh, I see.
Yeah.
Okay.
He didn't send it to Fox, I guess. I don't know why.
Okay.
Right, and then here, again, how fine-grained complexity helps how it guides us in finding new algorithms. So, if you consider this last algorithm, m plus n to the 1.9, then what we showed is a fine-grained reduction. We showed that if we can continue these improvements, maybe not even all the way down to a linear time, but just even m plus n to the 1.5. So if Gomer-Hu tree in simple graphs can be solved in m plus n to the 1.5, even slightly faster than that, then you would have a breakthrough in non-simple graphs, right? So it's a reduction from non-simple to simple. Then if you have a fast algorithm for simple, you get a breakthrough there. So you might as well just think about that problem instead of just getting incremental improvements. And indeed, we managed to do it. We showed an n squared time algorithm for Gomer-Hu tree in general weighted graphs, and later this was improved to a near linear time algorithm. Yes. So this is how fine complexity tools can help us design fast algorithms. Now, as far as the isolating cuts lemma, first I want to say that again it's been quite useful ever since its introduction. And
Wait, sorry. Can I ask you a question? So for the this linear time result, do you get just get the values of the cuts, or do you get the Gomer-Hu
the
tree?
Gomer-Hu tree itself.
The Gomer-Hu tree
Yeah.
for undirected graphs, and for directed graphs you just get the value.
It doesn't do anything.
Oh, what's simple and non-simple then?
Oh, I see. We go back. So this result was the first Gomer-Hood tree in any setting, even if unweighted, right, or even simple. And then the last one, what I showed here, is that even for the more general setting of general weights.
So
Simple and non-simple, just weighted and unweighted.
Yeah. Oh, so simple is slightly easier than unweighted.
Okay.
In unweighted graphs, you can have multiple edges, let's say.
I see. Okay. So simple is like
Easy.
unweighted, no parallel edges.
Yeah.
I thought it's undirected. Okay, so everything is undirected.
Everything is undirected, yeah.
I see.
Gomer-Hood tree exists, so.
So does this say anything for directed, or that's
I guess
we
what
come
is-
visit here next year?
Thank you. We're working on directed graphs.
But this doesn't directly imply anything for direct. Like the directed, we're still stuck with the quartic, or like not quartic, the omega plus one.
Yeah, for sparse graphs, I wouldn't expect any progress soon because the SATH situation. For dense graphs, it's different. It's more open. There's no strong conditional law about it. Isolating cuts lemma. So again, since its introduction, it's been used for many problems, not just all pairs max flow or global mean cut, also some others. Right. So this is the difficult example. I'm going to try to give you some taste of what the isolating cuts lemma. And how it can solve this difficult example. So again, we're given a graph. This is not the graph. We're given a graph. Then we're guaranteed that this is how its Gomer-Hood tree looks like. Right? We know L1, L2, and we know the identity of P, the root. And what the lemma says is that we're given a pivot and a set of terminals, let's say the blue nodes here, and we want to find the minimum cut from P to any one of those terminals. So just applying max flow algorithms, you would have to spend, let's say you have 17 terminals, 17 max flow applications, right? Or C, number of applications as the number of terminals. What this lemma says is that can do it much faster if some conditions hold. Specifically, you can do it in just log n applications of max flow, right? And the conditions that need to hold is that so if the terminal is the only terminal in its side of the cut, then you would get the correct value for it. So for example, again, we have the blue nodes, the colored nodes, they're going to be the terminals. So the minimum cut from P to X has only X in the side of X of the cut. So you're going to get the right cut for it, but not for U. For the terminal U, as you can see, you have another terminal in its side of the cut. And so then you're not going to get the right value necessarily for it. Okay, so this is what the lemma says. Let's assume also, to make our life easier, that this is the only Gomer-Hood tree of the graph. There aren't any other. Some graphs have multiple Gomer-Hood trees, so let's assume it's the only one. So these are the steps of getting the actual result for the isolating cuts in this setting. So in the graph G, again, not in the tree, in the graph G, we add edges of infinite capacity between the pivot P and every terminal. Okay? And what I want to claim is that it's not going to make chaos in how the Gomer-Hood tree looks like. So more specifically, more rigorously, u tilde is the only terminal in its subtree, then its subtree looks the same after this modification. Okay, and the proof sketch is that if it didn't look the same, if it looked differently, if there was another cut, not the one that was there before, then you could just remove the heavy edges that you added, and you would have gotten a smaller cut in contradiction, because we assume that there's only one Gomer-Hood tree. Yes, please.
Oh, 3 minutes.
3 minutes. Oh, okay. Right. Then in the second step, we repeat the following polylog n times. In G, we take P, we split it into two, P1 and P2. We add an edge of infinite capacity, a bigger infinite. Infinite is bigger, a U squared in this case. And then we reconnect the edges of capacity U, either to P1 or to P2 with probability 1/2, either to P1 or to P2. And then we find the minimum cut between P1 and P2. And so we repeat this polylog n times. The basic idea is that the nodes in L1 are going to go with their parents. This is basically the idea here. So the observation here is that the edge with the Gomer-Hood tree with this new edge contracted is the previous tree, is just that tree. And the second observation is that all terminals that we connected to P1, let's say, in the graph are going to be connected to P1 also in this tree, in the tree of the graph after modification. And again, the reason is that otherwise, if it was connected to the other pivot, then you would get a cut of higher capacity that you would otherwise get. Finally, if so for every terminal U tilde, you define S U tilde, the estimate of the isolating cuts, as all of the nodes that went to the same side in all of these polylog n applications. And then the observation is that if a node is a cut member, then it must have followed its parents in all of those. So every application of minimum cut, you get a lot of information at the same time about all of the cuts. Maybe you don't get precise answers, but you do get a lot. And then by applying it polylog n times, you would get that with high probability. Each one, you manage to separate each pair of those parents. Yeah, and if you have any question, please ask. And these are interests. Thank you.
Thank you. Additional questions from people who have not yet asked questions? or not, they can open it to people that have asked questions already. Yes, Sasha.
No, I was everything. I wanted.
At the very end, so I guess the goal is to find this matching, I guess, between the L1 and L2s. Is that what we think about? And so you're kind of randomly assigning the L1s and then doing this cut tells you how the L2s
Yeah.
split, and then that.
Exactly. Yeah, exactly. So each application, in each application, you have kind of half of the set of the L1 here and half of them here. The important part is that the grandkids are going to go in the same. Yeah.
You solve for that cut between P1 and P2.
Yes, exactly. The Gomer-Hood tree looks nice, and then this is why.
Okay, so I'm curious. So it seems very impressive, this new linear time or almost linear time algorithm. How practical it is? Like, because you convince us this problem is so important. I'm curious if this is quick to be implemented, and if this actually, how well is it? How easy is it and efficient to implement?
Well, you can see it as a proof of concept. And I don't think it has been implemented yet. It's very complex now, but still have hope.
Okay, let's thank Ohad again. And